hatches open underneath, so you can have a glance inside. These obviously will be closed normally in flight. And you get a good view of the wing shape here as well.
It's not small, is it?
No. Now this goes down the parachute, you can notice it's now from where the pilots sit. You can imagine taxiing this aeroplane around a curved taxiway while the wheels are on the taxiway. The cockpit is going to be right out over the grass. So it takes a bit of getting used to. The only reason it is so far back is because the fuselage gets narrower further forward, and there's a lot of equipment further forward as well. There isn't enough room to have it any further forward. And this does in fact retract forward, like almost all aircraft in the carriages. The doors open here, so they're closed with our heads. Then the carriage will retract forward, and then the doors will close. And these metal brackets around the front here are water deflectors, so that if it lands on a wet runway, at the point the wheels touch down, they don't make a great big splash of water up, which could be sucked into the engines. It gets deflected back down by those onto the tyres and prevents that from happening. By the way, those tyres might look a bit rough. You think, well, you wouldn't particularly want those on your car looking like that. In actual fact, they're only about halfway through their wear life. Those little cotton tufts are deliberate. They're sacrificial tufts, and they help to cut down the wear on the actual tyre itself. They're good for about 70 landings, and this pair we reckon have done about 30, so they're about less than halfway through their life. You can see the hydraulic cylinders here on the side, the nose wheel steering, the steer it on the ground, and various pipes for the hydraulics here as well. No brakes on the front wheels, all the brakes are on the main wheels at the back here. So if we move further back, we can see the underfloor baggage area here. See, it's not very big, but you can get some suitcases in there, not very many. The main baggage area is at the back, and I'll show you that when we get to the back of the aeroplane. Now we're standing here under the wing, this great big thin delta wing, where all the fuel was stored. Something like 26,000 gallons of fuel was stored in here when it was full. And if you come back here, we've actually got the panels open where you can see how the fuel was put in. You can see the attachments for the hoses here with these panels open, and the fuel, as you can see, it says on the door there, is Jet A1, which is standard jet fuel, the same as any other aircraft fuel. And this other panel here is the fueling control panel, which is used by the ground engineers when they're fueling up the aeroplane. And there are a row of 13 fuel gauges there for the 13 tanks in the aeroplane. 6 in this wing, 6 in this wing, and a big tank in the tail. And the big tank in the tail was used to balance the aeroplane in flight, because one of the characteristics of having a wing which has got such a long chord, so long from root to tip as this one, is that as the aeroplane's speed varies, the lift on the wing moves around an awful lot. The faster it goes, the further back the lift on the wing goes. And to keep it in balance, you need to shift some of the aeroplane's weight back to balance that as you accelerate. And that was done by the engineer pumping fuel from tanks in the wing through to that big tank right in the tail. And conversely, on slowing down at the other end, that fuel would have to be pumped back as the centre of gravity moved forward, the centre of lift moved forward, to keep the centre of gravity coincident with the centre of lift, to keep the whole thing in balance. And something of these 26,000 gallons weighs about 95 tonnes. And of that 95 tonnes, about 10 tonnes was used for weight transfer to keep the aeroplane correctly balanced. But it was all usable as fuel as well. At the end of the flight, all the fuel will be in the wings, none in the tail, so the whole lot was usable by the engines. There was no fuel wasted just for weight transfer. It was all usable by the engines.
What was the maximum range then?
Well, 4.5 hours at 1,350 miles an hour, so 5,000 miles, something like that. Here's the main undercarriage, much more substantial than the nose wheels because it's taking most of the weight, much bigger tyres. These are good for about 30 or 40 landings. You can see that because of the sheer size of this assembly, it's not going to retract into this very thin delta wing we've got. It has to go sideways into the base of the fuselage here. So after takeoff, these doors here in the base of the fuselage, these swing open. The two undercarriage legs go up towards each other like that, and then the doors close. And in fact, you can see these round shapes on the doors approximate to where the tyres are when the undercarriage is retracted. And in the centre of each wheel set, in fact, if you come around this side, you can probably see it better. In the centre of each wheel set is a little silver three-bladed fan, electrically driven from the cockpit. That was mainly used to cool the carbon fibre brakes on landing, but it was also used to cool the wheels and tyres during taxiing and during takeoff, because the takeoff speed was very high, about 250 miles an hour, so these tyres got very hot during the takeoff run and they needed to be cooled. The engine intakes here These are square because they've got a bit of work to do on the air before it reaches the engine. The air coming in here is going about twice the speed of sound. The engines can't take supersonic air. No jet engine can. It has to be subsonic. And that's what this intake does. It slows the air down from twice the speed of sound to about 350 miles an hour in about 11 feet, which is the length of the intake system. Not only does it slow the air down, but it also highly compresses it. Because you've got a load of air coming in here very fast, and you slow it down, you compress it. So the thin air at 60,000 feet gets very highly compressed, very dense air, and also heated if you're doing that. So you get very hot, very highly compressed air fed onto the face of the engine, and that's what the engine wants, that's what makes it efficient. This works up to about Mach 1.3. After that we have to start changing the shape of the intake by moving these ramps down, which have danger written on them, to keep the shock waves, which actually slow the air down, in the right place. And if there are two things that made this aeroplane work, one is the shape of the wing, and the other is the design, this intake, and the onboard computer control system that controls these ramps to keep the shock waves in the right place to slow the air down. Very important part of the aircraft's propulsion system. On the side, it shows us what the engines are. Rolls-Royce Sceptre Olympus 593. There are 4 engines, they're still in the aeroplane, everything's still in the aeroplane, nothing's been taken off since it arrived here, it's all complete. The engines are mounted in pairs, there's 2 on this side, and they're side by side. There's one here, there's one next to it, 2 on the other side, and they start about where the red line is and go back. 2 Rolls-Royce Olympus engines developing 40,000 pounds of thrust each. Fairly simple 2-shaft turbojets, nothing particularly special about the engines apart from the fact they're very good basic engines. The really clever bit is the intake, and to a lesser extent the nozzle system on the back. You can see the colour here changes because we go from aluminium construction of the whole aeroplane to titanium here, because this got too hot to be aluminium, so this was made of titanium, which is why it's a different colour. Yeah, difficult to machine as well. So get to the back here, you can see the variable nozzles on the back of the engines, the 4 eyelid nozzles. Those have a couple of purposes. One is they can actually vary. If you look at the ones on the far side there, you can see they're actually pointing towards each other. They're called converging nozzles. They're pointing towards each other, compressing the gas flow. That's the subsonic setting. When you go supersonic, you need to change that to a diverging nozzle to get the gases out faster. And that's when these change. The top ones move up, the bottom ones move down, and they change their orientation to a diverging nozzle to get the gases out quickly. And their other function, of course, is to provide reverse thrust after landing. When the top ones swing down, the bottom ones swing up, and they redirect the gas flow forward over the wing and under the wing to slow the airplane down on landing. The control surfaces here are all hydraulically powered. These are what control the airplane in flight. You can see the fairings under the wing. These have got the hydraulic rams in them that move the powered flying controls. And of course they're all drooped down because there's no power on the aeroplane. Once the power came on and the hydraulics came live, these would level up with the back of the wing and move following the pilot's controls in the cockpit to control the airplane in pitch, nose up, nose down, and in roll side to side. For your nose left and right, there's a conventional rudder on the back of the fin. And then finally, right at the back, are the 2 little wheels which extend and retract with the main undercarriage, and they're there just to protect the back end of the aeroplane during the landing and taking off so it doesn't touch the ground. And last of all, I'll mention the baggage cabin. You can see this door with the red writing on it. That's the entrance to the baggage cabin. The door over the back of the wing marks the back of the passenger cabin. You can't get any more further back than that. That's the entrance to the baggage cabin. The space in between the 2 doors is the baggage cabin inside, and the space behind that door backwards is where that large fuel tank is, I mentioned before, for balancing the airplane in flight. Anybody got any questions?